So here on the top side, left hand side and right hand side, two types of dimensioning style are shown. Left hand side, positioning dimensions are correctly managed, like correctly drawn. So the position of this hole, how I know this is its hole or not, because on the this is front view and that's top view, and in front view I'm seeing here at the center we have center line. So that's why, and on the side of the center line is dash line. That means this is a hole. So this is a hole. So hole center is shown with from reference from edge, and horizontally is 20, 20, and okay, 24, and vertical line, like the vertical dimension is 20, horizontal dimension 24. And here we have there are no hole, but on top of the parallelepiped we have another parallelepiped or another box. So that box edge is referred from the bigger one, from bigger one to the smaller edge. We have two sizes. One is 16 and one is 12. But if you on the right hand side, there are two similar parts are shown, and that is front view, and that's top view, and that's front view, and then that's the top view. And if you write dimension, if you draw the dimension as shown on the right hand side, that's wrong, because in this view 38 is shown wrongly, because the references are invisible, like it has a dash line. So you should avoid to draw to define dimension in the view which is not shown. Like the view, the features are hidden features, so do not add dimension in hidden features. Okay, so instead of this one, so you can choose a view this as a top view. In the top view you can add this dimension like 38. That's correct, because we can see easily this from the top, there's two holes, and then you can define write the dimension here. So use visible views to add dimension. So that's correct, that's wrong. And below you can see three types of definition of circular dimensions, positional dimensions of the circles. On the left hand side, first we draw two vertical and horizontal center line, and then by referring this cross point center, we draw another circle with using chain line like this. Then we refer this circle as a center to make the center for small circles. So small circle center will refer this big circle. But we have to spread this one equally, so it should be 5 holes with equally spaced. So we can write like this way, and we can write 5x means we have same 5 holes, and those 5 holes have same diameter 17.4. and another word, equally spaced means in between them are equal spaces, equal angles. So we know that what's a circle angle. Circle has angle 360. It has 360 degree, and 360 degree equally spaced for 5 angles. So we're managing 5 sectors, and then we're dividing 360 degree to 5, that is 72. And then we're measuring from vertical axis 72 degree, and then draw like this way. central line, and crossing of these two chain lines are giving us a center for the hole. So one hole and another, okay, from here then to here, another 72-degree, then crossing will make us to center for the circle, another 72, and then find the center and draw the circle, and then draw the circle. Okay, but what's giving is this diameter of this circle, 89, and then diameter of small circles, 17.4. So 5x is 5. Diameters are same and equally spaced, means the distance between this vertical one and between, you know, this central line. So the lines which is going to the center to find a center for the small circles. Okay, so if you do not write equally spaced, so then you need to show distance between them, like in the middle. It's shown like this way, 69, and that's the distance or between them is not equal. 35, one is 55, one is 69. So you need to show from the reference to this another second reference should be shown a distance or angular distance. And again, diameters are same, so that's why it's written 4x, diameter 17.4. So 4 of them are same diameter, has the same diameter. On the right hand side bottom, we have 3 holes are given, and the hole locations are shown like this way: vertical dimension, horizontal dimension, vertical dimension, horizontal dimension, from vertical or horizontal center lines, vertical dimension, horizontal dimension, and also drawn like this circle with a chain line, and then shown as a diameter 3.5. That's wrong because we already defined by using x and y vertical and horizontal dimensions the centers for the small holes, and this is not needed. So then that's why it's written over dimensioned. Okay, so for one feature, if you can define, that's it. Do not add any other dimension. The whole diameters are same, so that's why it's written 3x, and then diameter sign, and then value. Okay, so if you have symmetric shapes, we can use this kind of method. So from the center to the another center, from left to the right, so draw like this 120 distance, and diameter 50, and the center horizontal like this line, and from the bottom to this horizontal center 22, and general overall vertical dimension is 44. And we can draw like this way the radius, only one radius, another second radius is not shown because it's symmetric. We have symmetricity line center, and also the hole is shown like this way with a legend. It's written 2 holes, diameter 10. So another hole you can keep without anything, because you know you already mentioned that there is 2 holes. So 2 holes are same dimension with 10 millimeter diameter. So R3 means this, there is a fillet, there is another fillet R3, and so on. Okay, and on the right hand side it's written like this way: 2x, 2 holes are same diameter with 22 diameter. So, and then this is upper arc is 2x again, so this side, and on the another side, left hand side, so because with R 28.5, same thing. So that's why this is not showing. In the bottom, you see distance between 2 lines are shown 20, and this radius of this arc is already given. So from here you can take it. Okay, so that's why 2x are something does not need it, because you know this 20 is shown already, so this will be a radius with 10, so you don't need to draw here this one. And if you draw like here, like this one arc 20, so that's it. So you don't need to give this distance between horizontal distances, and distances between the centers are shown like 98. So on the contour is shown like radius R28, so you don't need to show any other side because they're symmetry. And here 25 to the left hand side, 25 to the right hand side, and we have the radius, and then from the center radius 116, 116, and distance between them is equally like 1905, so like bean shape. And then here the radius 2x or something is given. So here over dimensioning examples are shown. If you have on the top view, if you have a symbols like diameter symbol 6.3, diameter of this hole is 6.3, and then this is a depth symbol. Depth is 16, so you don't need to show then this 16 again in different view. So that means you already mentioned here. And here, like overall dimensioning is given 2.86, and from this reference, from the left hand side reference, so 0.62, and then another chain dimension 1.62 is given. So you don't need to show the last one. Okay, so if you draw last one, so that will be over dimensioning. Whether this one, we should take this one, whether 2.86, so one of them should be eliminated. For the vertical one, also similar. Overall, if the overall dimension is given, and you need to show only one here, one should be deleted. Or if you wish to remain this one, so then overall dimension should be deleted. Or you can write in overall dimension the brackets on the both side, like that means in the bracket, the values in the bracket means reference value. So dimensions are consist from primary dimension and secondary dimension. The bracket means secondary dimension. Secondary dimension is just for information, for just seeing it, not for making it. Okay, so on the right hand side we have radius, 4 radiuses, actually 0.5 millimeter, and 0.5, actually that might be an inches, 0.5 inches. And if you have 4x written here, so that means 3 of them should be deleted, eliminated, otherwise that will be over dimensioning. Same thing happening in the bottom, like line center here, from center is from right hand side there is 20 millimeter, and then from here we draw an arc with radius 28, another we draw with radius 20, and then if we reach horizontal line, and we'll measure from this center, okay, to the right hand side 20, and from this 20 we're measuring 62, and then draw this vertical line on the left hand side. And if you add here 22, that's wrong, because you know we already know this, because 20 is 20, okay, 62 we have, and 20 we have already. From 60 minus 20 we have 42. From 42 minus 20 again 22 we already have, so you don't need to add here. Okay, and here tapers, how to draw the taper. Actually taper has several parameters like length, and then like truncated cone size, like taper. One bigger side is given with x, smaller side given with y, length between them, and then theta angle, we have slope angle between them. And instead of giving these 3 values and 4 values, actually we can give only one of them, one diameter and one length, and then a slope number, for example taper angle. Okay, so 0.25 means there is a 20 like this way. So the formula x minus y divided by length. Okay, so if x is given, if the length is given, and if a taper is given, so y can be calculated. Or if one of them is not given but others are given, so you can calculate it. For example, alpha degree, okay, theta degree is given, theta divided by 2 tangent times 2 give us a taper. If the taper is given, and you can calculate theta degree. If the theta degree angle is given, so then you can calculate a taper. And if the taper is given, and if x is given, for example, big D given, small d given, and L distance is given, so you can draw it and you can calculate even angle between them. Or D is given, L is given, so small d is not given, and angle like this 0.25 by 1 is taper is given. So we can calculate an angle and we can calculate a small d. If big D is given, L is given, and theta angle is given, so we can calculate a small d. Okay, so with using this kind of information, the taper might be given. It might be a fraction 1 by 4, 1 by 4, and then sides of slope is going reducing, and it might be given this kind of fraction 0.25 by 1. Same thing. Okay, 1 by 4 and 0.25 by 1 is same thing. So where it came from? So the bigger side here is x is 20, and y is 10, and divide by length. So that is 10 by 4, 10 by 40. So that means 1 by 4. Or if you divide this one and calculate it, that's 0.25. So 0.25 by 1, that means a taper. Same thing, 25%. So there is a symbols. There are symbols are shown. So that means the first from the left-hand side top, that's counterbore or spot face symbol. Second one is countersink symbol. Third one is depth symbol. Depth symbol, like horizontal line, like this, and then an arrow is shown like this way. Okay. Then the fourth one is a reference, so brackets, arc lengths. Okay, so counterbore and countersink, what's the meaning? Counterbore is like this hole. Okay, so there is a hole here hatching. To install the bolt inside of the part. Okay, so this kind of hole calls counterbore. Okay, and when you're going to show it, so you don't need to add many dimensions. Like, do we have counterbore? Yes, here. So this is a counterbore hole. So we have bigger diameter, smaller diameter, and then depths. So 3 dimensions value with values with extension line should be shown in reality. But instead of this one, you can write like this way. Just small hole, just bold hole, diameter is shown like 21. Written can be written C bore, diameter 33, so diameter 33 is bigger hole, and then times 18 deep. Same thing happening with this one. Okay, so instead of this one, just you can draw like this shape. That means contour bore hole, and then you can write diameter sign and then diameter of this. So diameter instead of C bore label or characters, so you can draw this symbol and then write it 33, diameter 33, and then 18 deep depths. You can use this symbol. That symbol means depths. Yeah, like here, 6.3 depths 16. That means this one. And arc length is this. If you have an arc, like this arc, so we have this kind of horizontal distance, horizontal dimension. For example, this is 100. So that means the distance from this edge to this edge. But how about the length of this arc? So in this case, we need to have the longer distance, right? The distance is longer. So for example, 106 on 110. So then on the top of this, if you draw like this thing, like this arc, that means this is length of the arc. Okay, so length of the arc is 106. But if you do not have this one, that means that is the distance from this point to this point. So distance of this line. Okay, so that for that one, you need to use this symbol. And slope symbol is this one. Dimension origin. So we already have seen this one, running dimension. So the beginning place, reference should be started from this point. For this one, 157. For every dimension, every horizontal dimension, the origin should be started from here. That's a symbol. That symbol. Dimension origin. Conical taper. So taper we already seen. Okay, so taper symbol, same like here. Square shape. If you have a dimension value, and before the dimension value, if you have this kind of square shape, that means this is other dimension also similar. For example, here, yes, here square, and given one side is shown with dimension 14, and before 14 is shown like this way, square shape. So other dimension, other side also same 14. Okay, the meaning, because this shape is square shape. So place is times. Okay, so just like this X character. Radius, you already know this, big capital R character. SR means spherical radius. So if you have instead of circle, if you have a sphere shape, so you can write like SR and then the value. That means this shape is sphere, and then its radius is given value. And so here you can see various using of the symbols. For example, diameter shape, the lower value is 9.4 and upper value 9.8. And depth symbol, and then 20 millimeter. And from this one, we can understand from this one to up to here is 20 millimeter. And diameter of this hole is 9.4 to 9.8. So that's a tolerance. For example, here, if you have this kind of shape, and then if it's shown like this way, symbol, square shape, and then 6, that means this is square shape, and this is not cylinder, this is a square shape, and then the side value is 6 millimeter. Slope in the civil engineering might be shown like this way, like 1 meter to up and 1.5 meter to the side, or 1 millimeter. Okay, so one unit, I mean, it might be 1 meter, might be 10 centimeter, it might be 10 meter to 15 meter. Okay, so it might be a meter, 1 meter to 1.5 meter to the side, or 4 meters to up and then 1 meter to the side. So here, countersink. What's the difference of counterbore and countersink? Countersink is like this hole. So hole to screw or to install it here, a countersink screws. Okay, and it has a smaller diameter and it has a bigger diameter. It has an angle, this angle. And so it's shown like this way. 6.5 means smaller diameter. Through means it's open hole. And this symbol is countersink symbol, so angle. Or the meaning is countersink, like this symbol. It's not straight like here, this one. And then diameter is shown here, this big one, diameter 10 millimeter. And then angle is 90 millimeter, 90 degree. Leaders. So leaders are like these lines, which is showing and helping us to show smaller distances, like small dimensions. Like if there are no room to write the value, we can use a leader. Okay, so if a slope, again, to write there a value is difficult. So that's why we can do like this legend, and then legend might be finish it with horizontally, and then on the horizontal line we can write the value. There's various ways you can see. But here, in this example, it's shown leader is with polishing recommendation, but if you use very small angle to draw a leader, that's wrong. Okay, so it should be enough angle. It's better to use 60 degree, 45 degree, okay, and more than 45 degree. It might show many information. So dimensioning and arcs are used like this way. So we need to show the center to give the arc radius or radius. Okay, so that's the best way. But in some cases we might not show the center. So then how to find this? In this case, we will have a tangent lines, like vertical and horizontal lines are tangent here, and then is using this information. So we have radius 6, so you can write parallel line from vertical and horizontal contour, and then crossing place will be a center for this arc radius, arc center. Okay, in case of there are no place to draw a center, or your page might be small to draw true center. So then we can make like this false center. So just you can put somewhere the center and then bend like this line and draw like this line. Okay, so bend it and right here 7.5. That means radius, and that means false center. So it's a radius is like this, but the real center is not here. It's here somewhere here, but we don't have a place to draw this. So that calls false center. So dual dimensioning. Dual dimensioning means you can use in both unit of measuring, like millimeter and inches. Millimeter dash inch, millimeter over inch. Okay, so on the upper side is given millimeter, and on the bottom side is given in the bracket inches, or on the upper side millimeter and below inches. Okay, on the left hand side the slash is given millimeter, and on the right hand side inches. So in the brackets. Okay, contour ball hole, countersink one, like small diameter, bigger one, angle, and then depth here. This is spot facing. Spot facing is before installing the bolt or nuts, we are preparing to installation of this. So we are flattening the surface. So that means spot facing. Curvacings can be shown with many radiuses. And these arc radius reference points should be shown regarding to from some reference point. From, for example, from here, 20 here on the left, and then we can draw the R80, and then this reference is given 30, and then another one. So here, so draw like this, and then to draw this one, we can show this reference 55, and this point from this one we can draw another arc. So this calls radiusography. So with using many radiuses, we can generate curves. Or a different way is like set of many points can be given like this way, and to show this coordinates of these points might be given vertical and horizontal dimensions. It might be shown with many dimensions like this way also, this combined way, vertical, horizontal dimensions, and arc dimensions and reference values. Okay, so where is the center of them? And if you use a similar shape things, but many times, so you don't need to draw them for everything. Just draw it and write there A, B, C, D, E, F, G like parameters, and then give a table, and then write there what's the A, what's the B, what's the C, D for part number 1, part numbers 2, 3, 4, 5. Okay, so that's possible. Another way, like chess table, you can write like this way. If you have many information, many whole information on the plate, like sheet metal, you can do like this way. Start from one reference, like right here 0, and then horizontal and vertical values can be written in specific places, like which is showing us the center of the holes. And then draw here 4x, so there are 4 holes like this, 8 holes are like that, and 16 holes are like that. Okay, and show information about these holes. Okay, so that's a way of give definition of dimensions. Thank you very much. So we have a 10-minute break, and then later on we can continue as to make a lab class. Okay, thank you very much.
In this video, we are going to learn about dimensions on engineering drawing. We are going to look at what dimensioning is, what are the elements of the dimensions, and what rules for dimensioning are. Furthermore, we are going to look into dimensioning methods and look what functional and non-functional dimensions are. Imagine that you are buying a new cabinet online. You are looking at the pictures of the cabinet, and you are satisfied with its form and aesthetics, and you would like to buy it. As you are limited with the space, you are looking for the dimension of the cabinet to see if it will fit in your space. At least what you will look for is width, depth, and the height of the cabinet. The next logical step is to measure your free space and compare it with the defined cabinet dimensions. If the cabinet does not fit in your free space, you will not purchase this cabinet. The similar thing we are doing with the components that we are manufacturing. When we create a drawing of the 3D object, we create all the necessary views, orthographic views, and/or pictorial views, for its unambiguous representations, and we add dimensions to it. Then, we send this drawing to our supplier to manufacture it. After components have been manufactured, we would, or our supplier, inspect the components' dimensions to see if they are created according to our drawing specification. In case some of the dimensions are outside of the specified dimensions, supplier will have to rework the component or create a new one. Properly defined dimensions ensure that everyone involved understands the size, shape, and tolerances of the object being depicted. Furthermore, they guide machinists and fabricators in determining the appropriate tools, techniques, and tolerances required to produce the part accurately. Accurately defined dimensions help convey the design intent. It provides information about critical features, relationships between different parts, and important geometric characteristics. Dimensioning for those reasons is the most important part of the drawing creation. The dimensioning can get very complex as the complexity of our product gets higher. You could have 10, or more, different components as a part of one complex assembly. These components could be fixed to each other, while others could move in respect to each other. Defining proper dimensions to be inspected and defining the proper tolerances is one of the hardest parts of creating the engineering drawings. These concepts will be explained in another video because they are so important that they will need a few videos to be completely clarified. But before we go to these complex topics, first, we must learn the basics. Elements of dimensions. As we previously mentioned, dimensioning is necessary to define the shape and form of an engineering component. In other words, with the use of dimensioning techniques on the engineering drawings, we define physical boundaries of the component like size and location of the different features. On a drawing of thin lines with the arrows on the sides and the number in the middle, or on side, is how we represent dimensions on the engineering drawings. The rules for the dimensioning are defined by ISO 129-12018. In the real world, most engineering companies use CAD software for designing products and for creating engineering drawings. Most of CAD software already contains different standard rules for creating drawings. With that being said, we will not dissect every rule to its core. At this point, I think that it is good enough for you to learn the basic terminology of dimensioning and then move to perfect your craft of dimensioning drawings unambiguously. Extension line, dimension line, nominal value, and terminators. Let us now look at the most important elements of dimensions. Extension lines are drawn perpendicular to the feature that is being dimensioned. Dimension line. The dimension line is perpendicular to the extension line, and above this line, the nominal value is shown. Nominal value represents the nominal value of the dimension, i.e., it represents a physical value of the feature in specific units. The nominal value is always above the dimension line, and it is in a natural scale, 1:1. The tolerances are always added to the nominal value. Terminators. On the engineering drawing, we are using terminators to clearly represent the end of the dimensional lines. In ISO 129-12018 you can see recommended types of terminators. As you could imagine, the sizes and shapes of all of these elements are defined by ISO 129-12018. But as I already told you, all of these rules are already incorporated in the CAD software, and as long as you choose your preferred standard in the software settings, you should be fine. In addition to the elements mentioned before, we can also encounter the following elements. Leader line used to direct a dimension, note, or symbol to the intended place on a drawing. Reference line is created in conjunction with the leader line. Property indicators, symbols, are used to replace words to simplify the drawing. Property indicators, symbols, are diameter, radius, square, spherical diameter, spherical radius, arc length, thickness of thin objects, depth, cylindrical counterbore, and countersink. Reference letter is used when we have alternate dimensions for the different usage. For example, we have the exact geometry of the plate with two different hole diameters. In that case, we don't have to create a new drawing with the different hole sizes, but we can mark this dimension with the capital letter. Then, the letter would be placed in the table and the values for the different hole sizes. Rules for dimensioning. While defining dimensions on the drawing, we should keep in mind rules for dimensioning. All dimensions on the drawing should be in the same specified units, example, millimeters. If we use other units for specific features, the corresponding unit should be written with the nominal value. All the relevant dimensions of the object should be defined on the drawing. Each feature is dimensioned only once on the drawing. If we need to dimension something twice for informational purposes, we can use auxiliary dimensions. The auxiliary dimensions are placed into parentheses. The comma should be used as a decimal separator. Dimensioning methods. Now when we understand the basics, let us investigate the methods we can use when we are dimensioning the shape and form of our objects. Chain dimensioning. Chain dimensioning is the method where dimensions are placed from one feature to another feature. This method is commonly used. We should keep in mind that each tolerance builds on the next one. This method is usually used when the parts function requires that the features are related to each other. When using chain dimensions, it is important to provide clear references and maintain a logical and consistent order. Proper alignment and spacing of dimensions are essential to avoid confusion and ensure the accurate interpretation of the chain of dimensions. Parallel dimensioning. In the parallel dimensioning method, all the dimensions originated from the same base. This method is commonly used for machine parts. Also, it is used when the size or feature should be controlled from a common reference plane and less tolerance buildup is desired. When employing parallel dimensions, it is important to ensure that the dimension lines are not excessively long or extend beyond the feature being dimensioned. Proper spacing, alignment, and consistent placement are key considerations to maintain a clear and organized drawing. Running dimensioning. The running dimensioning is exactly the same as a parallel method, but a different graphical representation is used. Dimensions are placed in a continuous manner along an uninterrupted length or feature, typically along the edge or centerline of an object. Running dimensions are commonly used for dimensions along linear features, such as lengths, widths, and heights. It is particularly useful when there are numerous repetitive features or when dimensions need to be placed in a compact and organized manner. The starting location of the dimension is defined with the origin symbol. Combined dimensioning. The combined method is the practice of utilizing multiple dimensioning methods within a single engineering drawing. By combining different methods within the drawing, we aim to optimize clarity, readability, and space utilization, while providing comprehensive and accurate dimensions for different aspects of the design. Equally spaced features. By combining different methods within the drawing, we aim to optimize clarity, readability, and space utilization, while providing comprehensive and accurate dimensions for different aspects of the design. When features are equally spaced, we can simplify dimensioning one and write how many times it is repeated. Repeated features. When we have multiply features with the same dimensions, we can dimension only one feature and note how many times this dimension is repeated. Symmetrical object. When we have to dimension symmetrical object, we can simplify the drawing by creating only half of the object and indicate the symmetry line. Dimensioning of restricted areas. When we need to define special requirements to a restricted portion of the feature, for example, surface hardening, we have to indicate that area on the drawing. Dimensioning chamfer. Functional and non-functional dimensions. When we are dimensioning an object, naturally, some dimensions will be more important than others. Some dimensions will be critical to the correct functioning of the component, and these are called functional dimensions. Other dimensions will not be critical to correct functioning, and these are called non-functional dimensions. Functional dimensions are obviously the more important of the two and, therefore, will be more critical when making decisions about the dimension value. Dimensioning on the engineering drawing is probably the most challenging part of the drawing creation. You can see that there are many dimensioning basic rules, and that is not even the hard part. The next step to upgrade your dimensioning skills is to learn about the tolerances. With time and practice, these rules will embed in your work routine, and you will not think about them. When that happens, make sure to rewatch this video. As a real expert, you want to make sure that you are communicating the right message every time someone checks your drawing. You are not only communicating design details on your drawing, you also communicate your expertise and your company brand. With that being said, make sure that you always communicate the right message.